Welcome to the Explainer. Have you ever looked at a block of text or maybe just a list of words and realized there's an entire hidden mathematical universe just waiting to be uncovered right beneath the surface? Well, today, we're taking a seemingly standard text-based coding problem and drawing out its hidden visual blueprint. We're going to see how a simple word game actually teaches us a profound lesson in system mapping. Let's get into it.
Okay, so here's the challenge. How exactly do you transform a starting word, let's say red, into a target word like hit by changing exactly one letter at a time? Oh, and the catch? Every single intermediate word you create along the way absolutely has to be a valid word from a specific dictionary we provide. No making up gibberish. To demystify this whole thing, we'll follow a clear roadmap. We'll cover the word transformation challenge, visualizing the invisible graph, finding the shortest path, the bidirectional search optimization, and finally, space and time complexity.
Section 1. The Word Transformation Challenge. Let's lay out the rules of the game.
We're given a start word, red, an end word, hit, and an array of valid dictionary words. Now, the constraints here are tight but super clear. All the words are the exact same length, they only contain lowercase English letters, and there are absolutely no duplicates in our dictionary. And hey, if we can't find a valid sequence under these strict constraints, we just return a length of 0.
Just look at how our starting position is framed. Because each transformation can only alter one single letter at a time, the word red can only initially branch out into a few valid options. If you check our dictionary, changing the first letter gives us bed, changing the middle gives us rad, and changing the last, that gives us rod. These are the immediate neighbors of our starting word.
Moving right along to Section 2. Visualizing the invisible graph.
This right here is a massive aha moment because it's where we realize we aren't just dealing with basic strings of text anymore. If we take a step back and draw direct connections between every single dictionary word that is exactly one letter apart, this invisible map suddenly emerges. Notice how the words literally become nodes, and those one-letter differences, they become the connecting lines or edges. So bed connects to bad, rad connects to rat, and so on. The whole thing is interlinked based entirely on that single-letter rule.
So the really crucial takeaway here is that our tricky text-heavy word problem has just beautifully transformed into a geometric graph routing problem. The challenge is no longer about blindly guessing words. It's simply about finding the shortest path from the start node, red, all the way down to the target node, hit. You can see that winning path highlighted perfectly right there.
Section 3. Finding the shortest path.
Now that we actually have our map, how do we write an algorithm to navigate it and guarantee we find the absolute shortest route? Well, on an unweighted graph like this, our absolute best friend is breadth first search, or BFS. We rely on this level order traversal to explore outwards step by step. Imagine tossing a pebble into a still pond. The ripples expand evenly in all directions, right? That is exactly how this search works. It guarantees that the very first time we hit our target word, it is mathematically certain to be the shortest possible path.
Let's see how this actually builds. Starting at distance 0 with red, our search ripple expands to the immediate one-letter neighbors at distance 1, which are bed, rad, and rod. Then it pulses outward again to distance 2, grabbing nodes like bad and rat. You can really see how evenly it searches across the entire breadth of the graph. The ripple just keeps expanding. We hit distance 3, finding bat and hat. And finally, at distance 4, boom, our search locates the target node, hit. Because we started counting our distance from 0, we just add 1 to include the starting node itself, which gives us a total shortest transformation sequence length of exactly 5 words: red, rad, rat, hat, and hit.
But wait, how do we actually do this efficiently in code? Generating that entire visual graph beforehand in memory, comparing every single word against every other word would be incredibly slow. So to optimize our memory, we completely avoid building a massive adjacency list. Instead, we just store a dictionary of valid words in a HashSet. That gives us lightning-fast O1 lookups. Then, during our BFS, we take our current word, swap out each letter from A to Z on the fly, and just check if that newly generated word exists in our HashSet. Simple, right?
All right, Section 4, the bidirectional search optimization.
Breadth first search is great. It definitely gets the job done, but there's a brilliant twist we can apply to find our shortcut even faster. With a standard BFS, we expand massive ripples all the way from the start node across the whole graph until it finally hits the end node. But think about this.
Why search all the way from point A to point B, expanding this huge, wide search area, when you could just start a search from both ends simultaneously and simply meet in the middle?
By alternating our progress in the code, meaning we push one level out from the start node and then we push one level out from the end node, we drastically reduce the total number of nodes we have to explore. It's a real game changer because the search trees stay incredibly shallow and narrow rather than growing exponentially wide.
So how do we know when we're actually done? It's super elegant. We just keep track of the visited nodes for both ends using two separate hash sets. The exact moment a word generated by one search ripple appears in the visited hash set of the other search ripple, we know our two ripples have collided. Just like that, we instantly have our shortest transformation sequence. We simply add the depths of both searches together, +1, and we're done. And that brings us to our final section, Section 5, Space and Time Complexity.
Let's break down the mathematical efficiency here so we can really understand why these design choices work so well. The time complexity is O(n times L squared). Let's unpack that really quickly. N is the number of words in the dictionary, and L is the length of those words. For up to n words, we're checking 26 letters across L positions. That takes L steps. And then, hashing that newly generated word to check our hash set takes another L time. Hence, L times L, which gives us that L squared factor. As for space, it's O(n times L because we need to store our dictionary and our visited nodes in memory.
Now, here's a totally fascinating quirk about big O notation. Even though our bidirectional traversal optimization shares the exact same theoretical big O time complexity as standard BFS, in practice, it is vastly more efficient. Because the search trees meet in the middle, the widest, most time-consuming part of the search is completely skipped. That means your actual code is going to run much, much faster in real-world applications.
As we wrap up this explainer, I want to leave you with this thought. This wasn't just about changing the word red to hit. Mastering this specific problem teaches us a universally applicable skill. It trains our brains to recognize hidden graphs in the systems all around us. I mean, if vocabulary words can be navigated exactly like cities on a map, what other complex systems in your work or even your life are just nodes and edges waiting to be discovered and optimized? Keep looking for those hidden connections, and I'll see you in the next explainer.